Okay, good evening, everyone. Today's topic is masonry structures. Um, those who has been participating in this program know already this is a very extensive training program offered by International Code Council. It has been going on for a couple of months, uh, and those who have joined um, recently, um, you can probably access the other lectures on concrete and steel structures over YouTube. That will be facilitated by ICC. Uh, Today's topic, masonry structures. I know most of the engineers in our community, they're not very interested about these type of structures. Actually, when I request my students to do some research or work on masonry structures, most of them are very, very reluctant to do so. But actually, in our country, most of the existing building stock are of this type, masonry structures. I'm not saying that this type of structure is important for new buildings. Actually, most of the new buildings are concrete structures, not masonry structures. But we should be aware, or we should be rather careful about these types of structures. So we should have some knowledge about the code provisions that we should follow while designing or construction of this type of structures. So uh, let's start. So in Bangladesh National Building Code 2020, masonry structures are covered in three different parts. Part 5, Chapter 2, Section 224 deals with the material standards of different components of masonry structures. Part 6, Chapter 7 is the main chapter for design aspects of masonry structures, and some of the construction aspects are also mentioned in this chapter. And part 7 deals with the different construction related issues like storage of different components of masonry construction, and some construction safety related issues in part 7. Today, I'll focus mainly on part 6, chapter 7, uh, although I'll refer the standards mentioned in part 5, chapter 2. Part 7 and other construction related issues will be somewhat covered in a coming lecture that will be on 15th July of this month, the 15th. So that will be related to construction safety particularly, but we'll discuss some other issues too in that session. So we'll discuss mostly part 6, chapter 7. So the topics that I'll cover related to masonry structures, the components and their standards, basic design requirements, then the allowable stresses. I have changed the order in my presentation. Actually, in the code, allowable stresses are discussed first, and then basic design requirements are introduced. But for the convenience of presenting or explaining, I have made the order like this. First, I'll discuss the basic design requirements and then the allowable stresses. Then, very short mention of design of unreinforced masonry. Then, design of reinforced masonry. Uh, uh, I think I should mention here that in our country, there is almost no reinforced masonry. We don't have the practice of this type of construction. reinforced masonry. And most of our masonry construction are unreinforced masonry type, which is very, very vulnerable to earthquake. Then the stability requirements, some basic stability requirements. Then we'll discuss strength design for slender walls and shear walls. Remember, the basic design philosophy for masonry structures is based on working stress design method, but for slender walls and shear walls, a designer can adopt strength design method too. Then we'll discuss about some important issues of earthquake resistant design of this type of structure. Very brief mention of strengthening of masonry buildings for earthquake. Remember that in the building code, in other chapters like chapters on concrete or steel, there is absolutely no mention of retrofitting or strengthening. But since for masonry buildings, strengthening is very important. We are not very much interested to build new masonry structures. Rather, most of our focus is on conserving the existing masonry buildings. So strengthening is important from that point of view. Then another new concept for us, but it has been practiced for quite a long in other countries, the concept of confined masonry, which is earthquake. This type of construction is less vulnerable to earthquake. So discuss these topics. Now, the components, the basic components that are used for masonry construction, particularly for reinforced masonry, are masonry unit. So we'll discuss the different types of masonry units. So these are basically blocks or bricks. Then mortar, cement mortar, lime mortar, the material that we use to provide the joints between the brick units. Then grout, this is used for reinforced masonry, like for hollow brick or hollow block. When you use hollow blocks, we fill the hollow part by grout, using grout, cement grout. Highly workable or almost flowable material. Then reinforcement, regular reinforcement is used with hollow bricks or hollow blocks. You can see the picture on the right hand side that reinforcements, vertical reinforcements are provided in the hollow cells of the hollow blocks, and those cells are filled with grout. Then metal ties and anchors. Anchors are used to tie the masonry walls or columns with foundation or with other concrete or stiff members. And metal ties are mainly used in multi-width or multi-limb or multi-leaf, like cavity walls, where we have two layers of bricks. They are called width or limb, and we leave a cavity or gap between those two limbs, and these limbs are connected with metal ties metal ties that are used in certain spacing. So let's see what different types of masonry units that can be used. There are different types. These 4 types are mentioned in our in part 6, chapter 7. The first type is the common brick that we always see. So you see a picture of the machine cut brick. There could be the traditional brick with frog mark. That kind of brick can also be used. These are clay bricks, burnt clay bricks. We have our own standard for that, which is BDS 208. Then there could be hollow bricks. Uh, in Bangladesh, these are mostly ceramic clay bricks with hollow bricks. We have a separate standard for this type of units, that is BDS 1263. We can use facing bricks that is also made of burnt clay. Facing bricks are used on the surface of concrete or other masonry walls, on a masonry wall or a concrete wall, for the purpose of decoration or ornamentation of the surface. They are not load bearing; they are ornamental. These are facing bricks. Then, very important is the last type, hollow concrete blocks. So concrete blocks, this is quite useful for reinforced masonry. Uh, these concrete blocks, uh, in Bangladesh, engineers are not always very interested to use the concrete blocks because they think that they have low strength compared to bricks. But these concrete blocks, if they satisfy the strength requirement, they are very, very useful, because you see the grooves um, on top of the concrete block. You can place reinforcement along these grooves, and you can place vertical reinforcement through the cell, and you can grout the cells. So this type of blocks are very useful for reinforced masonry. Okay. And they are environment friendly too, because burnt clay is not very friendly for our environment. So that's a different story, but I think most of you are very much aware of that. That burnt clay is quite damaging for our environment. Now, that was about masonry unit. And now let's talk about mortar. I think we should keep in mind that mortar is the most important part of masonry, because the strength of the masonry work mostly depends on the strength of the mortar, because mortar is the weakest, or the joints are the weakest part of masonry. I think you all know about this, and that's why we have to be very careful about mortar strength. Now, depending on the cement to sand ratio, mortars are classified in different grades. So there are 6 standard grades. M1 is the highest grade, or the strongest one, where cement sand ratio is 1:3. And we have M2, M3, M4, M5, M6. M6 is the leanest or the weakest grade, where cement sand ratio is 1:8. Now you can understand the ratio by adding just 2 with the grade. Like for M4, the cement sand ratio will be 4 plus 2, 1:6. And the minimum prescribed compressive strength is mentioned here. So we'll see how we can make sure that the compressive strength satisfies these values by doing some tests. We'll talk about that test. So these are the mortar grades. Now grout to fill the cells of hollow blocks. There can be 2 types of grouts. One is fine grout and another is coarse grout. In fine grout, we don't use any coarse aggregate. In coarse grout, we use fine aggregate and coarse aggregate too. So the cement to sand ratio for fine grout is usually 1:3 or like that. And for coarse aggregate is 1:5, where 2 parts of the 5 parts is coarse and 3 parts among 5 is fine. So coarse aggregate, we have to classify this because this is important, when we'll decide about the clear spacing between bar, rod, and masonry unit. So for fine grout, we can spare less spacing. And for coarse grout, we have to leave greater spacing. So for that, we need to know what type of grout we are going to use. Reinforcement, any ordinary reinforcement we can use, like it can be deformed and plain billet steel bars, which is the most common type we have, which is ASTM A615. The ductile type are ASTM A706, which is low alloy steel deformed bars, like uh, the ductility class D steel bars, for example, 500 DWR or 500 DR. Um, those are ASTM A706 type rebars. So we can use ASTM A706 or normal type ASTM A615. The wears are also available, 6mm or less diameter rebars. Wears are also available in our country, and epoxy coated rebar can also be used. So all types of rebars can be used as reinforcement. Now, metal ties and anchors, as I was saying, that they're used for anchoring the brickwork with foundation or with any other um, stiff walls like concrete walls or concrete column, steel column, etc. So they're used for those purposes. And ties are also used in multi-limb or multi-width cavity walls to connect two widths or limbs of brickworks of the wall. Now, let's talk about basic design requirements. So, as I said, that the basic design philosophy is working stress design. So, for masonry, the court's recommended design method is working stress design method. So, naturally, the stress strain relationship that is considered is linear stress strain relationship, and second order effects are not considered. That is, the eccentricity is considered to be very small, and there are provisions which try to make sure that the, there is very small eccentricity of loading on the wall. Now, there are some geometric parameters that we have to understand first before going to decide about before going to talk about the design formula. For example, we'll talk about height, effective height. For different support conditions, the effective height of a wall or a column will be different. Now, remember, there can be masonry columns too. Masonry does not have to be only walls, there may be columns. Now, the distinction between wall and column is just the length to thickness or width to thickness. Width and length is the same thing in this context. Length to thickness ratio. If the width or length of a masonry work is less than 3 times the thickness, then that is column. If it is more than that, then that is wall. Now, depending on the support condition, the effective height will be different. If the wall is continuously supported at the bottom and at the top, then the effective height is same as the wall height. But if, for example, you can see the figure on the right hand side, right side, there is a steel beam on top of the column, and there may be very light roof like truss or other light roof, which is not giving continuous support to the wall. in the direction out of the plane of the wall. Sorry, it is giving support in the outward direction, out of the plane direction, but it is not giving any support in the in plane direction. So in the in plane, along the plane of the wall, the effective height is twice the height of the wall. And in the out of the plane direction, since there is a support, the effective height is equal to the height of the wall. For column, it is always the case, the second case, that is, for columns, we will not consider continuous support. We'll consider only this type of concentrated support. So for columns, it is always in one direction, it is always twice the height of the column. Now, if there are openings, then the definition of height will be different, effective height. For example, on the left side of the picture on the left, there is continuous support, but there are openings. So in the plane of the wall, for the continuous support, the effective height is height of the wall. And out of the plane, the effective height will be 75% of the height of the wall plus 25% of the opening, taller opening, or the opening having greater height. 25% of that will be added to the height. Remember, if we increase the height, we will have slender column, or slenderness ratio will be higher. So if we have greater height, that means we are being more conservative. In the second case, on the right side, there is no continuous support and there are openings. If an opening height, if the height of an opening is more than half of the height of the wall, then the effective height will be twice the height of the wall along the plane and out of the plane of the wall. Okay, so this is important. But if the height of the opening is less than half of the height of the wall, in that case, in that case, out of the plane of the wall, the effective height is same as the height of the wall. And along the plane of the wall, the effective height will be twice the height of the wall. So there's another provision I didn't draw any picture for that, but you'll find that if you see the code. That was effective height. Now we also need length, the definition of length, effective length. There may be 5 different conditions. On top left, you can see that the wall is continuous and is supported by cross walls. And openings are away from the cross wall by a length of 1/8 of the height of the wall. In that case, effective length will be the shortest one, which will be 80% of the length of the spacing, center to center spacing of the cross walls. So that will be the effective length, 80% of the length. This is the shortest one. You remember, the longer the length, actually, that will increase the slenderness ratio. So that's more conservative. So in the second case, on top right, we can have cross wall on one end and continuous on the other side. In that case, the effective length will be 90% of the spacing between the cross walls. Third one is at the middle, where we have cross walls on both ends. Then the effective length will be the length between the cross walls. Fourth case is at bottom left, where we have one free end and the other end is continuous, supported by a cross wall. So in this case, the effective length will be 1.5 times the length of the wall from the free end to the cross wall, location of the cross wall. And the last case is at the bottom right, where we have a free end and the other end is supported by a cross wall. So in this case, the effective length is twice the length between the free end and the cross wall. So these are different cases where effective lengths are defined in different ways. So we have talked about effective height, effective length. Now we'll talk about effective thickness. Effective thickness is basically the nominal thickness of the wall. But in case of cavity wall, you can see the second case on top right, top right one. There, this is just a cavity wall where we have two leaves of walls or two limbs. In different standards, it is termed in different ways. Even in our code, sometimes it is called width, sometimes it is called limb, and in other standards it's called leaf. So we have two limbs or widths of or layers of brickwork and cavity in between. This is called cavity wall. So in case of cavity wall, the thickness, effective thickness is summation of the thickness of two limbs, T1 plus T2. In many cases, we can have piers or pilaster. Pilaster or pier is a kind of stiffener where in certain locations we thicken the wall to give support, lateral support. So when this type of pilaster or pier is used, the pier thickness is termed as TP, which is summation of the thickened part. The total thickness of the thickened part is called TP, pier thickness. If we have pier or pilaster with a cavity wall, then pier thickness is the thickened part, is the thickness of the thickened part of one limb, the limb which is thickened. So it is shown in the picture at bottom right. So, but what are the effective thickness for these cases where we have pier or pilaster is shown here. So effective thickness is the thickness of the wall multiplied by a factor K. Now the K depends on two things. One is the LP by WP ratio, which is the center to center distance of the pilaster spacing, and pilaster width is WP. So LP by WP and TP by TW, that is TP is the pier width or pilaster width, that is the thickened width of the wall, and TW is the nominal thickness of the wall. So depending on these two ratios, we just multiply the nominal thickness of the wall with a factor K, and that is the effective thickness. So we have now the definition of slenderness ratio. For walls, the slenderness ratio for a wall is defined as the lesser of effective height to effective thickness ratio, or effective length to effective thickness ratio. Now we have discussed what is effective height, what is effective length, and what is effective thickness. So now we can calculate these ratios, and the lesser of the two will be the slenderness ratio of the wall. And there is a provision that for URM or RM, the slenderness ratio, for non-slender buildings, the slenderness ratio must be less than 20. For columns, slenderness ratio is always effective height to effective thickness ratio, because for columns there is no length, that is, length is very small, less than 3t. So slenderness ratio is effective height to effective thickness ratio, and for columns this must be less than 12 for masonry columns. We need another information, and that is related to loads. Loads will follow part 6 chapter 2, that is dead load, live load, wind load, earthquake load, what is defined in part 6 chapter 2. Those things were discussed previously in other sessions, so we'll just follow them, and we'll follow the load combination of working stress design or allowable strength design load combinations. So that is there. For calculation of stresses, we need the loaded length. For example, if on a wall there are beams and the load is coming to the wall through beams, then what should be considered as the loaded length for stress calculation? The loaded length will be loaded length will be the center to center spacing of the beams, but this cannot be more than width of loading that is shown in the picture, that is the flange width of the beam or the bearing width of the beam, plus 4 times the thickness of the wall. So this is limited to this value. So we can divide the load with the loaded length and the thickness of the wall, then we can get the stress in a simple way. But there will be other stresses too. And if we want to have a loaded length somewhat at a distance, at a depth below from the point of contact with the beam, then we can draw a 30-degree from the vertical line to calculate the distribution of load. So from the vertical, the angle will be 30 degrees. So then we can get the loaded length at a certain depth from top. Minimum design dimensions. This is very important. For load-bearing walls, the thickness, effective thickness of the wall must be greater than 250 millimeters, that is 10 inch. 5-inch walls cannot be load-bearing walls. If we want to design load-bearing walls, the minimum thickness has to be 250 millimeters or 10 inch. For parapet, the thickness, minimum thickness requirement is less, that is 200 millimeters. And for parapet, height of the parapet must be less than 4 times the thickness of the parapet. In other words, if we want higher parapet, then we have to increase the thickness. So those were basic design requirements. Now, what are the formula for allowable stresses? You remember, we will follow working stress design, so we'll define allowable stresses. So, but first we need to know the strength of brick unit. Like the cylinder test, by doing cylinder test, we can understand the strength of concrete, FC prime. Here we have FM prime, 28 days strength of masonry unit. That is just like cylinder. This is mentioned in ASTM E447 prism test. We can prepare a masonry unit sample by placing 5 bricks and with joints, bed joints, and this will make a prism. 5, in some cases we can make it by using 3 bricks or like that. The slenderness ratio is corrected in calculation that is given in ASTM E447. Usually 5 bricks are placed on with bed joints. So using UTM or any compression testing machine, we can apply compression, and we can determine the strength, which is FM prime, 28 days strength of masonry unit. Now, if we want to do the test before construction to ascertain the strength, to select the materials, like if the brick and the mortar that is appropriate for this construction, or does that satisfy the design strength, we have to test 5 masonry prisms and then take average. For testing during construction, we have to use at least 3 sets of prism for every 500 square meters of wall. But if in the design, if the design strength that is considered in design is 50% of the allowable stresses, then no test is required. So now what are the allowable stresses? The allowable stresses for axial compression, flexural compression, and other shear, etc., we'll see. But another important clause in the code is that if we don't take help of spatial inspection, then we have to divide all these allowable stresses by 2. That is, we can take only 50% of these allowable stresses as allowable. So if we have proper inspection at site, then these formula will give us allowable stresses. Now, for axial compressive stress for unreinforced masonry, for all these cases, they depend very much on the slenderness ratio. So this H prime by T ratio, this is the slenderness ratio, effective height by effective thickness. So you see, normally FM prime is the 28-day masonry strength, and for URM we are dividing these by a factor of 5. So factor of safety is like 5. Not only that, then we are subtracting this value depending on the slenderness ratio, and it depends cubically. So if our slenderness ratio is high, then it is reduced cubically, the allowable stress. So that is very important. For reinforced masonry, the same formula is used, but only the stress carried by the reinforcement is added here. Since we multiply this FA with gross masonry area, that's why in the second term, gross masonry area is divided in the formula. Actually, we multiply FA with gross masonry area to get the allowable force in case of reinforced masonry. Okay, then compressive stress in flexure. In case of flexure, the allowable compressive stress is 1/3 of Fm prime by 3. But this must be less than 10 megapascal. That is the high the the specified strength of M1 grade mortar. So the strongest grade of mortar, the specified strength is 10 megapascal. Since we know that the masonry joint is the most critical part of the masonry construction. So the strength is governed by the joint strength, and this cannot go beyond the strongest masonry grade strength. So that's why this limit of 10 megapascal. Now, allowable tensile stress. We talked about compressive stress. Now let's talk about tensile stress. So tensile stress tries to make the masonry units take the masonry units apart, right? The bricks apart. So the bricks can be taken apart from bed joint or from head joint. So depending on that, if the tension is normal to bed joint or normal to head joint, we have different allowable stresses. And we have different allowable stresses for solid units and for hollow units. Okay. And for M3 and M4 type mortar, so you remember there were 6 grades, uh, uh, grade M1 to M6. So M1, M2, the cement to sand ratio is 1:3 and 1:4. For those types, M1, M2, these are the allowable stresses. But for M3 and M4, that is if the cement to sand ratio is 1:5 or 1:6, then we have to reduce this values by 25%. So this is important. Actually, below M4, M5, M6 is seldom used for structural load-bearing masonry construction. Now, allowable shear stress. So we talked about compressive stress and then tensile stress, and now let's talk about shear stress. This is probably the most important type of stress, because in most of the cases the lateral loads are carried by shear walls, masonry shear walls in masonry construction. The shear stress for flexural members, where so that is due to the out of plane bending, the shear stress is given here, 0.083 root over Fm prime, and for reinforced masonry this is much higher compared to URM. This is 0.25 root over Fm prime. So, and the maximum limit is also 3 times than URM, 0.25 megapascal and 0.75 megapascal. Shear stress for shear walls, so in plane shear, URM for clay units and for concrete units we have different values. Okay. Those were for shear walls. These are the values for unreinforced masonry. For reinforced masonry, it will depend on the moment, in plane moment, divided by shear stress, divided by effective depth. That is, effective depth is the from one end to the reinforcement at the other end. We'll just calculate effective depth the way we do for reinforced concrete. Similar way we calculate effective depth. So M by VD. Now, if the moment is M by VD is less, then we have different formula. If the contribution of a moment is large, then we have some fixed values depending on Fm prime as allowable shear stresses. So, okay. For reinforced masonry, we can design in two ways. We can, for tensile stresses, we always depend on reinforcement. But for shear stress, we can depend on masonry or we can depend on reinforcement. So depending on our assumption, the allowable stresses are different. Now, those were the allowable stresses in masonry. Now, for allowable stresses in reinforcement, for tensile stress, compressive stress, and bond stress, these are the values. You see, we are quite conservative. This is working stress design. So naturally, the allowable stress is 50% of Fy for tensile stress, but you see the highest limit, which is quite conservative, 165 megapascal. So 50% of 60 grade steel is how much? 210 megapascal. That is if we consider 420 megapascal as 60 grade. So in that case, 210 should be the limit for 60 grade. But here we are quite conservative. We don't allow the allowable tensile stress more than 165 megapascal. So that is like 40% of Fy of 60 grade steel. So for masonry construction, reinforced masonry, we are quite conservative because we cannot depend on the bonding between the reinforcement and grout as we can depend on the bonding between reinforcement and concrete. The bonding will not be that reliable. That's why we're quite conservative, even for allowable stresses in reinforcement. So, and the other values you can see. Now, for modeling purposes, modulus of elasticity is important. So, actually, from prism test, we can find Fm prime, and depending on the Fm prime, we can calculate the modulus of elasticity, just like for concrete. Modulus of elasticity depends on Fc prime. Here it depends on Fm prime, but this is directly proportional to Fm prime. In case of concrete, it is root over Fc prime, right? It's proportional to root over Fc prime. Here it is directly proportional to Fm prime. So, okay. So we have all the basic information like basic geometric parameters like effective height, effective length, effective thickness. Based on these geometric parameters, we can define slenderness ratio. And then based on slenderness ratio, we can define allowable stresses. So no allowable stresses, then for design of unreinforced or reinforced masonry, we have to check with the applied stresses. So the actually applied stresses, these are quite common formula we use or always use. For unreinforced masonry, we will consider that as a homogeneous material. And based on that assumption, we'll just calculate the basic stresses. So for axial stresses, it's just force divided by area. For flexures, MC over I, and for shear force divided by effective area. You have to remember the areas as effective areas, where we'll use effective length and effective thickness to calculate effective area. So that's the only difference. So this is very easy. Then for reinforced masonry, again, things the same as what we do for reinforced concrete. Here the assumptions are masonry does not carry any tensile stress. So all tensile stresses will be carried by reinforcement. And the second assumption is reinforcement is completely bonded with the masonry through grout. So this assumption uh, is not perfect, but we take care of the imperfection in this assumption by lowering the allowable stresses in both in reinforcement and in masonry. Now the formula for calculating stresses, uh, simple, like what the same as the RC formula for axial compression is force divided by effective area. For shear force, same, V is equal to uh, Fs is equal to V divided by Vjd, or AV SV by FSD, same formula. All the formulas similar to reinforced concrete formula. Here, the spacing, maximum spacing requirement for shear reinforcement is D over 2, effective depth divided by 2, or 600 millimeters. Member subject, again, same formula. So for concrete, for masonry is half FC kgBD square, moment is equal to, and for steel is M divided by FSJD, Fs. So same formula, working stress design formula of reinforced concrete. Now, if we see how the reinforcements are placed, so you can see that the vertical reinforcements are placed in the cells of the hollow blocks or hollow brick units, and the horizontal bars are placed along the groove of the hollow blocks, and the vertical reinforcements are anchored to the foundation or to the slab, and usually hooks are used to anchor. And there are some specifications regarding these. We'll see that. So these are the arrangement, the way reinforcements are placed in reinforced masonry. So some requirements for reinforcement. The first one is maximum reinforcement size. We can go for quite a large diameter rebar. 35 millimeter is the maximum reinforcement size that we can use, so quite large. And the maximum amount of reinforcement that we can use in a cell is 6% of the cell area without splice. If we use splice for lapping purposes, we can double this percentage of reinforcement, 12%. Now, spacing of longitudinal reinforcement, this is similar to reinforced concrete. Spacing between two bars will be 25 millimeter or bar diameter. Now, clear spacing from a bar, a rebar, and the nearest surface of the masonry unit is 6 millimeters if we use fine grout, is 12 millimeters if we use coarse grout, because coarse grout contains coarse aggregate, right? So that the grout can be placed easily in between the rebar and masonry unit. That's why these limitations are there of clear distance between masonry unit and the bar. Now the clear cover. Now the clear cover is the distance between the reinforcement from the reinforcement to the outer surface of the masonry. That is the clear cover, similar to reinforced concrete. So the clear distance from reinforcement to the outer surface of the masonry is clear cover, we need to have adequate clear cover so that the reinforcement doesn't corrode with time. And it depends on the weather condition, the exposed condition. If it is exposed to weathering condition, that is in part 8, the weathering conditions are defined, severe weather conditions like that. If the weather condition is mild, then in that case, we can have 20 millimeters of clear cover. If the weather condition is not mild, in that case, we have to have 40 millimeter of clear cover. If it is below soil, when the outer surface of masonry is exposed to soil, then the clear cover has to be 50 millimeters. So these are some details. Now the stability requirements, so that is very important. This is very important. In case of masonry, since we are not in our analysis, we are not considering the second order effects, so we have to make sure that second order effects do not come, or even if second order effects come, they are not significant. So the basic requirement is that the height to width ratio of a masonry building cannot exceed 2. So height to width ratio is specified, and we have to stiffen the walls by cross walls or piers or pilaster. We have to stiffen the walls at regular spacing. So that will depend on the story height. If the story height is below 3 or less, then the thickness of the stiffening wall or cross wall has to be 100 millimeters or more. The least thickness will be 100 millimeters. For more than 3-storied buildings, the stiffening wall thickness has to be 200 millimeters or more. And the spacing is also given in this table, and the spacing will depend on the thickness of the load-bearing wall. Remember, in our code, this is a general table. In our code, load-bearing wall cannot be less than 200 millimeters. There is exception. If it is less than 200 millimeters, then we'll call it slender wall. If the wall is not slender, so the thickness of the wall has to be 250 millimeters or more. In that case, the maximum spacing will be 8, more than 6 meters and like 8 meters. So that's it. And height of story is also restricted. For like it must be less than 3.4 meters if the wall thickness is 300 millimeters. If the wall thickness is less than that, so it will be like at most 3.2 meters. So height is also restricted. So from stability requirement, we get the height of the building from height to width ratio of the building. So we get minimum thickness of the wall. Depending on the thickness of the wall, we get the height of the story from this table. And depending on the number of stories, we get the spacing of stiffening wall or cross walls. Now, that was all about working stress design of unreinforced masonry wall or reinforced masonry wall. But there is also strength design method, but that is particularly for slender walls and shear walls. For slender walls are defined when the axial load is much low compared to its strength. So if the load from wall and load from floor, PW is the load from the wall, so self weight, and PF is the load from the floor, that is live weight plus self weight, dead loads of the floor and beams, etc. PW by plus PF divided by the gross cross section is less than 4% of FM prime. In that case, we can go for slender wall design, and FM prime cannot be more than 40 megapascal. Now, in this case, we can go for slender wall. Again, even if we go for slender wall, the wall thickness cannot be less than 150 millimeters. So minimum wall thickness for a non-slender type of construction is 250 millimeters, but minimum wall thickness for slender type of construction is 150 millimeters. For slender type of construction, we have to check the design using strength design method. For non-slender type of construction, we have to check the design using working stress design method. Maximum reinforcement ratio in the case of slender walls must be less than 50% of balanced steel ratio. And we have to, here for slender wall, we have to indirectly take care of the second order effects. So we calculate the moment, mid-span moment of the wall by W is the lateral load, uniformly distributed lateral load, H square by 8. So we assume that is simply supported. Then we assume an specified eccentricity. And again, we have to calculate the deflection. We have to calculate the deflection, and then we have to consider the second order effect. Now, delta U. Now, how can we calculate the deflection? So the specified deflection is, we can calculate by these formula. So it will depend on the cracking moment. That is the moment that will induce cracks, tension cracks in the wall. So cracking moment, remember, slender walls will always have to be reinforced masonry. We cannot design slender wall for unreinforced masonry. So the cracking moment is defined as the section modulus S multiplied by the modulus of rupture, FR. There is a mistake in the code. I admit that there is a mistake in the code, that it should have been FR, but in the code it is written FY. So that is actually yield moment, S into FY. But M cracking should be S into FR, modulus of rupture. The table of modulus of rupture is given, but the formula is wrong in the code. It is written as FY. It should be S. It should have been S FR. Now, modulus of rupture is given as a function of FM prime, and there are different formula for solid masonry and hollow unit masonry. And it will depend if the masonry is fully grouted or partially grouted. By fully grouted, it is meant that all the cells of hollow blocks or hollow bricks are grouted. And by partially grouted, it means that not all the cells are grouted. Usually, only the cells containing reinforcement are grouted. So depending on if it is fully grouted or partially grouted, the formula for modulus of rupture are different. And based on the modulus of rupture, we can calculate the cracking moment. If the service moment is less than the cracking moment, then we have one formula, which is like the formula of a propped cantilever. And if the surface moment is more than the cracking moment, but it has to be less than the nominal moment capacity of the wall, in that case the formula is a little bit different. Okay, So using this formula, we can calculate delta, and with that delta, we have to multiply the axial force. Then we'll get the applied moment, ultimate moment on the section. So we are considering second order effect of slender walls in this indirect way. And then shear walls. For shear walls, design of shear walls, the 5 values, strength reduction factors. Since we are adopting the strength design method, the strength reduction factors are specified for axial load or axial load with flexure. The 5 value is quite low, 0.65, but we can take higher values if the axial load is less. For Fy less than 410 megapascal, that is not for 60 grade or 60 grade or higher grade steel. For higher grade steel, we have to go for phi equals 0.65. But for lower grade steel, and if the arrangement of reinforcement is symmetrical, then we can increase the value of phi if the axial uh, uh, if the axial load is less, actually. So if the axial load is less than 25% of axial load, if we consider balanced reinforcement, or 10% of the total capacity of Fm prime into effective area. If it is less than 10%, then we can increase the value of phi. For shear, it is even less, 0.6. And for shear 2, we can increase this value if the nominal shear strength is much higher than the shear stress coming onto the wall or column. The stress, shear stress, which corresponds to the flexural strength. The shear stress corresponding to the flexural strength, if the shear capacity is higher than that, then we can go for higher shear strength reduction factor. So now the nominal strength Fm prime, we get this value from Prism test, but the Fm prime cannot be less than 7 megapascal or cannot be more than 20 megapascal. Axial strength is the same formula as we use for RC columns. Similar formula. So that is the for axial strength. Shear capacity, it will depend again upon M by VD ratio, and the shear capacity is mentioned here in megapascal. Oh, no. So shear capacity is the Vn. We have to multiply Vn with phi, and these values are given as Vn divided by A root over Fm prime. So basically Vn is equal to 72 into A into root over Fm prime, and we have to multiply this with phi, then we'll get the shear strength. Okay. So for shear stress, the in-plane stresses, the capacity for in-plane stresses, we can calculate them with these formula. In case of shear walls, we may have to use boundary member similar to reinforced concrete shear walls. We may have to use boundary members. In boundary members, that we have to use ties with vertical reinforcement. Now, when we have to use boundary members, if the failure mode is flexure, in that case, the maximum extreme fiber stress, that is flexural fiber stress, is 0.2 FM prime, then we have to use boundary members to take care of the extreme stresses on two ends of the shear wall. When the failure mode is flexure, boundary members shall be provided to confine all vertical reinforcement whose corresponding masonry compressive stress exceeds 0.4 FM prime. And the maximum length of the boundary member shall be 3 times the thickness of the wall. So the length of the boundary member along the length of the wall, the dimension of the boundary member will be 3 times the thickness of the wall. Okay, and the capacity of the boundary element has to be 0.4 FM prime. And the lowest bar diameter that can be used in boundary members is 10 millimeter, and the maximum spacing of bars can be 200 millimeters. So those were some important points regarding design of shear walls and design of slender walls using strength design method. So we have talked about working strength design method for unreinforced masonry construction and reinforced masonry construction, and we have talked about the strength design method for slender walls and shear walls. So there are some more details in the code. Please look up the code for those details. We have just briefly mentioned some important points regarding capacity and regarding capacity and stresses that will come out of those structures. Now, very important part is earthquake resistant design. For seismic zone, for different seismic zones, we have different provisions for masonry construction. So those are given in detail in this section of the code. So for masonry construction in seismic zones 2, 3, and 4, this section is for these zones. So for seismic zone 1, you don't have to follow this specific earthquake resistant design provisions. Number 1, FM prime cannot be less than 10 megapascal. Remember, for shear wall, we mentioned that FM prime cannot be less than 7 megapascal, but for earthquake resistant design, FM prime cannot be less than 12 megapascal. This is somewhat similar to earthquake resistant design of concrete, where the concrete strength cannot be less than 3000 psi, 21 megapascal. So for masonry, it's 12 megapascal. And mortar must be of M3 grade or higher grade, M1, M2, M3. That is, cement sand ratio should be 1:3, 1:4, or 1:5. No linear mortar can be used. M4, M5, M6 cannot be used for earthquake resistant design. Those were for material. Provisions for seismic zones 2 and 3. We have different sets of provisions for seismic zones 2 and 3 and seismic zone 4. For seismic zones 2 and 3, vertical reinforcement of at least 12 millimeter diameter shall be provided continuously from support to support at each corner, at each side of each opening, at the ends of walls, and at a maximum spacing of 1.2 meters horizontally throughout the wall. So a lot of details. Number one, the bar dia. For vertical reinforcement, the minimum bar dia will be 12 millimeters. Number one. Number two, where to provide vertical reinforcement. At least this is actually the earthquake resistant design for unreinforced masonry. Even for unreinforced masonry, we have to provide at least these reinforcements. For reinforced masonry, we normally use reinforcement and we calculate what reinforcement will be needed. But these provisions are actually for unreinforced masonry, but we have to provide at least these reinforcement at specific locations. So that is mentioned here. Like where we have to provide reinforcement. At each corner and at each side of each opening. Suppose we have a door, on both sides of the door we have to provide reinforcement. We have a window, on both sides of the window we have to provide reinforcement, and at each corner we have to provide reinforcement. At the ends of walls, like the free ends of the walls, we have to provide reinforcement. And in between these locations, if the spacing is more than 1.2 meters, then we have to provide vertical reinforcement at every 1.2 meters. Okay, so at least one 12 millimeter diameter rebar has to be placed. That is number one. Number two, horizontal reinforcement. Again, the bar diameter cannot be less than 12 millimeter. And where do you have to provide horizontal reinforcement? At the bottom and top of wall openings. So if there is an opening at the bottom, like a window, at the bottom of the window, you have to provide 112 millimeter bar, and at the top, and shall extend at least 40 bar diameters. From the end of the opening, we have to extend the reinforcement up to 40 dB bar diameter. At least 600 millimeters we have to develop past the opening. And we have to provide the horizontal reinforcement continuously at structurally connected roof and floor levels and at the top of walls. So at the floor level, at the bottom, we have to place horizontal reinforcement, and at the top of the wall, we have to place horizontal reinforcement. At the bottom of the wall or in the top of the foundations when dowel to the wall. And they have to be dowel to the wall. We'll see those details. For seismic zone 4, all those requirements, that is the provisions that are mentioned in for seismic zones 2 and 3 will be applicable for seismic zone 4. Plus, additionally, other requirements are there. The sum of the areas of horizontal and vertical reinforcement shall be at least 0.002 times the gross cross-sectional area of the wall. So 0.2% of AG, this amount of reinforcement has to be provided both horizontally, some of the, so say 50% of this has to be provided as vertical reinforcement, and 50% has to be provided as horizontal reinforcement. Okay, so cross section. You have to take the cross section of a wall. Like for horizontal reinforcement, you have to take a cross section, vertical cross section. For vertical reinforcement, you have to take a horizontal cross section. And we are supposed to provide vertical reinforcement at the corners and at the side of the opening. So we'll calculate all those reinforcement And then if that is less, we'll calculate the vertical reinforcement provided as the provisions I have already mentioned. For those provisions, we will provide vertical and horizontal reinforcement. If summation of those reinforcements is less than the 0.002 times the gross cross-sectional area of the wall, in that case, we have to provide more reinforcement. The area of reinforcement in either direction shall not be less than 0.0007 times the gross cross-sectional area of the wall. So there is a minimum in each direction. The spacing of reinforcement shall not exceed 1.2 meters, both for horizontal and vertical, and the diameter of reinforcing bar shall not be less than 10 millimeters. So it's already, so in any case, even in case of ties for boundary element, the diameter of rebar will be 10 millimeter or more. But for horizontal and vertical reinforcement, it has to be 12 millimeters or more. And band, we have to place some concrete sections at some locations. These are called bands, some reinforced concrete sections. The band shall be made of reinforced concrete with FC prime not less than 20 megapascal, or reinforced brickwork in cement mortar not leaner than 1:4, that is M2. The bands shall be to the full width of the wall and not less than 75 millimeters in depth, at least 3-inch with 3-inch depth, and shall be reinforced. For seismic zones 2 and 3 and for seismic zones 4, there are different requirements for bands. Now we'll see. So here you can see the requirements. So there you can, at the floor level, you can see some, it's written bond beam, which is band basically. And the spacing of horizontal reinforcements are shown. The minimum requirements of center to center spacing are given in this chart, in this figure. Height limitation is also mentioned. Height cannot be more than 3.5 meters floor height, and at the side of the openings, the reinforcement specification for reinforcement, development length, 40 bar die is also mentioned. So all those details are shown in this figure. So that was earthquake resistant design of masonry. So remember again, so now basically for seismic zone 2, 3, and 4, we cannot make a purely unreinforced masonry. That is the traditional practice in our country. We don't use any reinforcement in masonry. But even if we want to build an unreinforced masonry building, at least these reinforcements have to be provided. If we do not go for reinforced masonry design, even then we have to use those reinforcements. So now you understand that traditional unreinforced masonry is not allowed in seismic zones 2, 3, and 4. So you have to remember that. Now, since the traditional unreinforced masonry is not allowed, then those who are already built, how to strengthen them? There is a table in the BNBC 2020. There are some guidelines, kind of guidelines. What has to be used? What types of materials we can use for strengthening? So it will depend on the seismic zone. If the building is in seismic zone 1, 2, or 3, or 4, depending on that, and depending on the height of the building, the strengthening arrangements are listed in this table. For example, if we say talk about seismic zones 2 and 3, up to 2-storied height building, we can go for masonry mortar not leaner than M3. This is true for all the cases. We have to use lintel and roof bands. Here you see where we have to use bands, it is mentioned. For seismic zone 1, we don't have to use any band, that is reinforced concrete sections. But for strengthening purposes, for seismic zone 2, 3, and 4, we have to use lintel and roof band. Vertical reinforcement has to be used at every corners and junctions of walls. Bracing in plan at tie level for pitched roof. For the pitched roof at the tie level, we have to use bracing. Similarly, for higher buildings, we have additional requirements. Vertical reinforcement and jambs of openings have to be provided, etc., etc. So relevant sections are also mentioned in this table. So for strengthening purposes of unreinforced masonry construction in different zones of different heights, we can consult this table and design accordingly. So those were different specific guidelines for unreinforced masonry, reinforced masonry, slender walls, shear walls, and then earthquake resistant design. Then we talked a little bit about strengthening of masonry construction. Now I'll introduce a new type of masonry construction. It is called confined masonry. This is actually the new addition to BNBC 2020. All other provisions were actually there in BNBC 2006, except that the mention of zones were different in the previous code, and in this version we have 4 zones. Apart from that, all other provisions are identical to the previous version. This confined masonry was not there in BNBC 2006. In BNBC 2020, this concept is introduced. Now, although this is new for our country, and I think we don't have any single construction of confined masonry in Bangladesh, but this is quite popular in Latin American countries and in some Asian countries where earthquakes are quite frequent. So you can see it looks as if like beam column frame system, but this is different. You can see that the members which look like columns, they're actually quite thin compared to columns, and they're placed at some critical points, like at the corners and beside the openings. And actually, they are not constructed like columns, although they are reinforced concrete. So the sequence of construction is like this. First, you make the brickwork. That is, you construct the walls and you leave spaces for column casting or this confining element. They are not all actually columns, they are confining elements. They act like their purpose is to confine the walls. So you see the column-like elements, their reinforcements are reinforcement cages in place, but there no concrete casting is done before wall construction. So you first construct the wall, and you have the reinforcement cage of the column, and then after construction of the wall you pour concrete in that space which is left for column construction. So this is somewhat similar the way we construct boundary walls. For boundary walls, we first make the brickwork, and in between the brickworks, we have some reinforcement and we pour concrete later. So this is similar sequence. So the basic difference between an RC frame and confined masonries we can see from this table. So for RC frame, we know that the main load-bearing members are beams and columns. But for confined masonry, the main load-bearing members are basically the masonry walls. In RC construction, the infill masonry walls are non-load-bearing. For confined masonry, the beams and columns, they are basically confining elements. Their main purpose is not to carry the gravity or lateral load, but to help the masonry wall to carry that load by confining the masonry wall. The beams are called tie beams and the columns are confining vertical members. The foundation for RC frame construction, the foundations are usually for shallow footing, isolated column footing. But for confined masonry, we have to provide masonry for the walls too, because the walls are basically the load-bearing members. So we have stripped footing instead of isolated footing for confined masonry. The third difference is that the sequence of construction that I have just mentioned. For RC frame, we construct the foundation and then column and then beam and slab, and later we make the walls. In confined masonry, after construction of the foundation, we have the reinforcement from the foundation for the columns, but we make the walls first and later we pour concrete of the columns. And after finishing up to the floor level, then we cast tie beam and slab. And then again, we make walls and then columns, and in this fashion. So what is the purpose? It has been found that in many past earthquakes that this type of construction of confined masonry performs much better than unreinforced masonry. So in places where we don't have the luxury to go for reinforced masonry, at least, or if the building owner cannot afford a regular RC frame structure, who would like to make unreinforced masonry, they can build this kind of confined masonry without much added expenditure. So that is the advantage. Now there are some architectural guidelines. First is building length to width ratio should not exceed 4. So not only width to height ratio, here width to length ratio is important. It should not exceed 4. The walls should be continuous up, that there shouldn't be any offsets. The walls should be on top of each other like load-bearing walls. So we cannot have walls in any place on the slab like we do have for RC frame structures. So we can place walls in between any place on the slab. We cannot do that in this type of construction. The walls have to be on top of each other. It should be continuously up. Openings should be placed in the same position. Again, this is also very restrictive from architectural point of view, that the openings of the first floor should be exactly at the same position of the openings of the ground floor, or openings of the second and third floor. In all the floors, the openings should be at the same position. At least two fully confined walls in each direction. So in each direction there has to be redundancy, that we cannot depend on only one confined wall in each direction. There has to be at least two fully confined walls in each direction. Minimum wall density and maximum building height. Now, what is wall density? Wall density is the area of wall divided by the plan area of the building. That is wall density. So for each direction we calculate wall density. So this is in the plan. If we see the plan, we see the area of walls, and that area divided by the total plan area is the wall density. So for seismic zones 1 and 2, there has to be at least 2% of wall compared to the plan area. And there is a height restriction for confined masonry type construction, that for seismic zone 1, we can have at most a 4-story building. For 1 and 2, for seismic zones 1 and 2. For seismic zone 3, the wall density has to be at least 4% of the plan area, and we can go up to 3-story building for seismic zone 3. For seismic zone 4, the wall density must be at least 5%, and we can go up to only 2-story building. So this is actually meant for rural construction, in rural areas where we commonly see unreinforced masonry type construction, 1-story, 2-story, at most 3-story buildings. For those cases, instead of building 2-story, instead of building unreinforced masonry construction, this is being encouraged. So this is something we engineers have to be aware of, and we should promote this type of construction for rural or suburban areas. Now, vertical and horizontal confining elements, there are some guidelines for vertical and horizontal elements. For vertical elements, as I said, at the free edges of each structural wall element, we have to place vertical confining element. At both sides of any wall opening within area of more than 1.5 meters square, if the opening for window or for door, if the opening area is more than 1.5 meters square, then we have to place vertical confining element like columns on both sides of the opening. Within the wall, if necessary, in order to exceed a spacing of 5 meters between the confining elements. Now, we have confining element at the edges, ends, or edges or corners, and then at the side of the opening. But if we have a wall extended more than 5 meters away from those confining elements, then we have to have an additional, an extra confining element. So the spacing of confining element, vertical confining element, cannot be more than 5 meters. At the intersections of structural walls, like corners, where we have cross walls at those locations, wherever the confining elements imposed by the above rules are at a distance larger than 1.5 meters. So, right, if the cross wall is at a distance more than 1.5 meters from another confining element, in that case, in the intersection, we have to have vertical confining element. If the spacing of the cross wall is less than 1.5 meters from another confining element, then we don't need a confining element at that intersection. Okay. So these are the requirements for vertical elements. Horizontal confining elements shall be placed in the plane of the wall at every floor level, and in a case with a vertical spacing of not more than 4 meters. And if we have more than 4 meters from one floor to another floor, then at every 4 meter we have to have a confining tie beam, horizontal confining element. Okay, if we see the picture again, this is it. So you can see the confining beams and columns. The columns are placed at the corners and at the side of the openings. If the opening size is open area of opening is 1.5 meters square or more in that case. And along the length of the wall, if there is the confining element must be at a spacing of 5 meters or less. And if there is any cross wall, in this figure we don't have a cross wall. If we had another wall on the perpendicular direction of any wall, then at the intersection we have to have a confining element if that intersection is more than 1.5 meters away from another confining element. Okay. And about the horizontal element at the floor level, at every floor level we have to have a confining beam or tie beam, and at a maximum spacing of 4 meters. So these are the rules. So we can build something like unreinforced masonry, but we have to have these confining elements. So that will make it confined masonry. So there are some more details for confined masonry construction. Confining elements should have a cross-sectional area not less than 0.02 meters square. Now, we say that we have to have a confining element, but what should be the area of the confining element? And what should be a minimum dimension? What percentage of reinforcement should be used? These details are there. Confining elements should have a cross-sectional area not less than 0.02 meters square, with a minimum dimension of 150 millimeters in the plan, or in the plane, not plan, sorry, in the plane of the wall. Along the plane of the wall, minimum dimension should be 150 millimeters, 6 inches. Okay, so you can understand this is much thinner than a regular column. The longitudinal reinforcement may not have a cross-section area less than 300 millimeters square. So total area of reinforcement is given, and not less than 1% of the cross-section area. So this is somewhat similar to RC, that we have to have at least 1% of the cross-section area of reinforcement and not less than 300 millimeters square. Stirrups not less than 6 millimeters in diameter and space not more than 300 millimeters should be provided. We have to use stirrups. For tie beams, the stirrups will be, diameter can be 6 millimeters, and they may be at most 1 foot apart, spacing of the stirrups. And then column ties. Column ties should preferably have 135-degree hooks. These are not a must, these are recommendations, preferably 135-degree hook. So at a minimum 6 millimeter ties at 200 millimeter spacing should be provided. So similar to stirrup, the minimum diameter of tie will be 6 millimeters, but the spacing will be much less, 200 millimeter. It is recommended to use 6 millimeter ties at 100 millimeter spacing, so half of that spacing in the column end zones, like near the column end. So like 1/3 of the column height should be should have closer tie spacing near the joints. So from these information, I think we can design confining elements, both beams and columns, because we have cross section, we have minimum reinforcement ratio, we have information regarding stirrups and ties, so we can design the confining elements. And some more details, like at the corner where we have a column, vertical confining element, and tie beam. So at the details of uh, developed bars at the corner are shown here. So the bar coming from the beams should be embedded, should be anchored in the other beam, and the development length should be at least 500 millimeters. The reverse will be developed or extended in the other beam by at least 500 millimeters. Okay, so that was on the top right, the figure on the top right, and the figure in the bottom is the joint between a beam and a column, how the hooks, anchors or hooks should look like. They are shown. So in both the cases, in case of a tie beam, the longitudinal reverse are hooked at the end for anchoring, and for columns, that is the vertical element, confining element, the longitudinal reverse are hooked at the top of the beam, beam column joint. So these details should be used in the detailing. Some more details for confined masonry, like what should be the spacing between brickwork and the reinforcement of the uh, vertical confining element. It should be 25 millimeters. So, and the clear cover should be 75 millimeters. So these are the details. Now you see the wall is first constructed. That's why the toothing is there. We know that the joints, we never align the joints vertically, so the joints are staggered. So we have a toothing pattern where we end the wall construction. So on both sides of the vertical confining element, we have toothing, and that gives anchorage or shear strength to the vertical confining element. So we pour concrete in between these two wall segments, and the toothing part actually hold the vertical confining member that gives the confining in through this type of toothing. At the end of a wall where we don't have toothing, or at the corner, we always flush the wall. At the end, we always flush the wall, and there we don't have any toothing. And at the end, again, we have vertical confining element. So where we don't have toothing, in that case, for confinement or for proper bonding with the vertical confining element, we use these kind of ties. So they're basically regular rebars, small diameter rebars. They're used as ties, and they're anchored within the vertical confining element, and they are extended along the bed joint of the wall. So at a regular interval, this kind of ties are provided at the end of a wall with the vertical confining element. So these are some details that are useful, like the joint between beams or tie beams, and the joint with the tie beam and the tie column, and the interface between wall and vertical confining element. So these details you have to remember. I think I am at the end of my presentation. So today my presentation was short. It's about 9:30 and I have finished my presentation on masonry construction. So if I go back to the beginning and the topics, so what we have covered, we have talked about different components which are actually masonry unit, mortar, grout, reinforcement, and ties or anchors. So those are the components. Basic design requirements we have discussed about the effective height, effective length, effective thickness, slenderness ratio. Allowable stresses, since we adopt working stress design, we calculate allowable stresses for axial stress, for for compressive stress from flexure, for flexural stress, tensile stress, for shear stress. We have all those formula for allowable stresses. Then for unreinforced masonry design, the formula are very simple. They are just for homogeneous material, the formula for homogeneous material. For reinforced masonry, again the formula are identical to reinforced concrete. There are some stability requirements like height to width ratio of the building, and there are some restrictions on height and restrictions like the spacing of cross walls, thickness of cross walls, things like that, etc. Strength design and for slender walls and shear walls, we adopt strength design method, and relevant provisions are given there, like allowable uh, strength reduction factor and uh, strength capacity, that is uh, uh, nominal. We calculate the nominal strength and we use 5 values to design to get the design capacities. Now the 5 values are quite conservative for shear wall design, that we have to understand. Then there are provisions for earthquake resistant design. These provisions are actually for unreinforced masonry. So we have to use some minimum amount of reinforcement even for unreinforced masonry construction for earthquake resistant design in seismic zones 2, 3, and 4. So that implies that a pure unreinforced masonry is not allowed for seismic zones 2, 3, and 4. That all of us have to understand that URM, unreinforced masonry, is no more allowed in BNBC 2020 for seismic zones 2, 3, and 4. Now, there are some provisions regarding the material that we can use for strengthening of masonry buildings for different seismic zones. And lastly, we introduced a new type of masonry construction, confined masonry, which are quite resistant from earthquake loading point of view, and their not that expensive, quite affordable, but we have to know the construction method and sequence of construction, and that is not difficult, not even quite difficult. So we can introduce this confined masonry, the concept of confined masonry, in our rural and suburban areas, and we can promote them. So thank you so much. If you have questions, please leave your questions in the chat box. I'll try to answer them. For some reason, okay, yeah. Probably there are some problems with sound. Now the question, first question I can find relevant question is that the internal framing system is beam column frame, and the external frame of the building is 10-inch unreinforced masonry brick structure of a 4-story building. How do we check the stability against lateral loading of the brick wall for this 4-story existing building? Is the frame system acceptable? How do we assess the structure? Usually this type of construction is very, very vulnerable to earthquake. This type of mixed construction is very, very, basically this frame construction and these load-bearing type of unreinforced masonry, they are not compatible from the sense that frame construction is quite flexible compared to unreinforced masonry. The allowable drift is quite large in case of frame construction compared to unreinforced masonry. So this is very difficult to proportion the stiffnesses properly between framing and unreinforced masonry construction. If the unreinforced masonry is only used as shear walls, then that is somewhat compatible. But if the unreinforced masonry walls are also used for the purpose of gravity loading as load-bearing components for gravity load, then this becomes very, very difficult, because in most of the cases it is found that due to lateral load, since the frame moment frame system is quite flexible, they experience a lot of drift or lateral sway, and that causes quite a significant amount of second order effect on the unreinforced masonry, and that is not addressed in the concept of unreinforced masonry design methodology. So as I've mentioned in the very beginning in the basic design requirements, that a basic assumption is that there is very small effect of eccentricity of loading. That is a basic design requirement of unreinforced masonry, and that doesn't hold in case of this type of mixed construction, mixed system of moment frame and unreinforced masonry. That's why even for the case of strengthening or retrofitting, this unreinforced masonry part is quite often dismantled and a new framing system is provided. If we have to have some unreinforced masonry, that can be used as shear walls rather. So that will be my answer to your question. Will you give us a single certificate of this total webinar? No, I don't think so. For every session you have, you can download a certificate after appearing at the quiz. Oh, the answer is given by Dr. Das, Prabodh. You will need to take quiz for each webinar and print the certificate for each webinar. So that's it. How to consider external walls to carry portion of loads. Any reference link about load path on masonry component? So I think you here by external walls, how to consider external walls to carry portion of loads. I see. So in masonry construction, you want to understand what is the portion of external load that will be carried by the external walls and what will be the portion that will be carried by the internal walls. If that is your question, then we usually go with the tributary approach, both for gravity load and lateral load. So for gravity load, that we go for tributary approach, like the load coming onto the slab. So half the span on each side from a wall that will be carried by the wall, gravity load. For wind load also, we go by the tributary approach that on each side, half of the span, the lateral load, wing load that is coming onto the structure that will be carried by the wall. So in that case, the external walls will carry half of the load. But however, for earthquake loading, the total base shear is divided among the walls based on their stiffness, based on their shear stiffness to carry the shear. So based on that, which is actually based on the effective area. So based on the effective area, we distribute the shear force onto the walls. You can actually model this by plane strain elements. If you use finite element method, then usually we use plane strain element as wall elements, and from the model you can get the stresses. If someone failed a certain quiz, Dr. Prabhuda has already answered that. Considering a boundary wall, what should be case 3 or case 5? So boundary wall, if we have stiffening members and if it is continuous, then of slide 8, for you mean for effective length, right? Yeah. So it will be for continuous case if you have stiffening members. So all the pictures that will actually guide you. So if you have a very small boundary wall without any continuity, then if you have only one end and the other end is continuous, then you have case 5. And case 3 is if you have a very small boundary wall with both ends, stiffening members only at both ends, then you will have case 3. If you have stiffening members at certain spacing and the boundary wall is continuous, then you have case 1. How do you evaluate the material strength of an existing structure? Is it possible to do a prism test? This is a very good question. On a load-bearing wall that already exists? Yes, it is possible. In that case, you have to use some jack to usually we you have to use some jacks to retain the load, number one, for prism test. If you want to take out a prism from an existing structure. Sometimes we can depend on the truss mechanism of the wall. That is, even if you take out a single brick, the wall doesn't fail because the stress is distributed by a truss mechanism. But if you want to take out a prism, then you have to first place a jack to take the load, number one. But uh, for existing structures, shear strength is very important. For that, we use a different type of test. We use a flat jack, and we take out a brick and one or two bricks, and we place a horizontal. We place a jack horizontally. Sometimes it's called flat jack, and on the we put pressure on a brick. On the other side of the brick, we also take out a brick. So we have opening on the other side. So when you put pressure on one side of the brick is the stress comes to the joints. And when it fails in shear, then we can understand the in situ shear strength of the brickwork. So we have some shear test, but that is not mentioned in BNBC. That is mentioned in other in AC 41. This type of test is mentioned, shear test on existing masonry construction. Can you please update us if we will be shared the recordings later? Yes. Dr. Prabhuto, are you there? So is it all the lectures are already uploaded on YouTube or not?
No, we're in the process of doing that. It is not complete, but it will very soon, yes.
Okay. So you'll know when the lectures will be uploaded. You'll be informed.
We'll probably, yeah, we'll very likely send an email out to everyone who registered for one of these webinars in this webinar series.
Okay. Okay. Great. Thank you. How do you evaluate the material strength of mortar and existing structure? Is it possible to do a prism test on a load-bearing wall that already exists? The same answer. I've already answered this question. So can you tell when we can consider brick wall as a strut in the FEA modeling? What are the criteria? Right. For infill walls, we model the infill walls as a strut. There are guidelines in different publications, different AAC publications, different FEMA publications, there are guidelines. So for infill walls, in moment frame system, the infill walls are modeled as struts, but not the load bearing walls. We cannot, we can estimate the effect of stiffness for lateral load using a strut model, but in general, we cannot use only a strut model for load-bearing wall system, unreinforced masonry, because unreinforced masonry also take gravity loads. So gravity loads and lateral loads, all those loads are considered to produce in-plane stresses. That's why plane strain elements are used in modeling. I think the slides are slightly different from the uploaded ones. Sorry, every time I keep on modifying the slides until the very last moment. Sorry for that. I'll share these new slides. A little bit different probably this time. Yes, the handout was just okay. Sorry. Dr. Prabhupada has already answered. Where to put band for seismic design as it is all the bands are mentioned in the table for strengthening of unreinforced masonry construction. For strengthening, we have to provide at the lintel level, at the roof level. So at each lintel level and roof level, we have to provide bands. So that's according to BNBC 2020. But there are other publications where we should also provide bands for seal level too. So for the time being, if we follow just the BNBC at the roof level and lintel level, we have to provide band. Oh, please give an example of wall density. I don't know if you can see. If you can see, let me try to annotate. So, sorry. Okay. This is the pen, right? Pen. So I have to pen. Yeah. So can you see? I hope you can see. So suppose this is the plan and we have some walls. These are the walls. And we have some rooms, some walls going like these. We have some walls like these, probably some walls here, some walls here, some walls here, something like this. So if this is the width of the building plan, floor, and if this is the length of the floor, I should write F. So total plan area of the plan is WF multiplied by length of floor, and the wall area is the hatched portion. Only the hatched portion. We are looking at a plan, floor plan, and these are the wall. And the total summation of the wall area is say AW. So this is AW. Then wall density, say call it DW, is area of wall divided by total plan area. This is density, wall density. Okay, we can segregate wall density in different directions. Wall density along x direction, wall density in y direction. But in general, wall density is the total wall area in a plan, floor plan, divided by the total floor plan area. So that is wall density. I think the design of foundation of mason structure is missing. Yes. There are some guidelines regarding that. In the foundation chapter, you have all the necessary information regarding strip foundation. Okay, so basically masonry foundation will be strip foundation, and all the relevant information regarding that is given in chapter 3, part 6, chapter 3. What is the recommended compressive strength of concrete while constructing confining element in tooth wall? There's no information in the code for that. No, there is. Sorry, there is. It is written 20 megapascal. So 3000 psi. 3000 psi is the recommended minimum compressive strength of concrete. Is there any plan for the session on dynamic analysis of structure? Probably not this time. Hopefully in future there will be further webinars, and probably that will be, I'm not sure yet, but probably that will be offered by Engineering Staff College. So in that program, there may be dynamic analysis of structure, one session for that. Any analytical software to analyze masonry structure? No, actually, you can use any finite element, any software based on finite element method where you can model the walls, masonry walls at plane strain element. That is where all the stresses are in plane stresses. Out of plane bending is ignored in that type of analysis, but through some hand calculations, some out of plane bending is checked. But from capacity point of view, it is assumed that all the walls act as shear walls. For masonry wall, there is, and for dynamic analysis, sometimes discrete element method (DM) is used. There are some very good publications for dynamic analysis, discrete element method (DEM). DEM. Discrete element method is used for this type of construction, but that's too complicated. So for normal design purposes, that is not used. For masonry wall, there is a common problem, which is cracks on plaster. May I know the reasons for the unexpected cracks and how can we avoid it? Yeah, because of different coefficient of thermal expansion of the plaster, that is plaster mortar, and the background material, which is wall. Now, for normal brick wall, this is not usually a problem. Burnt clay brick, this is not usually a problem, but for concrete blocks, sometimes this is a problem. The mortar, they are not, the thermal coefficient of expansion of mortar, plaster, and concrete hollow block, they're different, and that's why sometimes this type of crack appears. But the manufacturers nowadays of hollow concrete blocks, they are taking this into account, and they are taking measures so that the new blocks do not show this type of problem. Any analytical software to analyze masonry structure? Have already answered these. What is the difference between WSD and ASD? In working stress design, in WSD, what we calculate? We calculate allowable working stresses. We don't calculate the ultimate capacity. We always calculate allowable working stresses. But for ASD, in steel, I understand your question is regarding to allowable strength design. For allowable stress in load combination, there is no difference. For load combinations in part 6, chapter 2, the load combination is same for WSD and ASD. But for steel, ASD, by ASD we mean allowable strength design, which is different from working stress design. In allowable strength, we always calculate the nominal ultimate capacity, Rn, just like for LRFD, load resistance factor design. So we calculate Rn, ultimate capacity, and then we divide this by omega to check the service loads. So that is the approach. So this is quite similar to basically ultimate strength design. Instead of multiplying with a strength reduction factor, we divide it with some safety factors, and then we check with the service loads. In WSD, we never calculate this. We calculate some allowable stresses. Okay, so that is the main difference. Can we use steel stiffeners rather than RCC confining elements? Probably we have to do some research on that. Probably already there are literatures on that. I don't know, but this is not there in the code. There's no provision for steel stiffeners for confined masonry. I don't know. Not according to the code. We can do some research on that, but I don't know what will be the advantages for that. Is there any code provision for number of story in zone 1? The only provision is height to width ratio cannot exceed 2. The height can be double of the width of the building. And the tables, there is no table that mentions anything for more than 5-story building. So implicitly, if we have to follow the tables, the maximum masonry building can have a height of 5 stories. That is implicitly all the tables. There is no table which mentions masonry construction for more than 5-story buildings. What is the specification about solid concrete block of different thickness? I have to check, but all those specifications are mentioned in part 5, chapter 2. So here in part 6, chapter 7, only 4 types of masonry units are mentioned: burnt clay solid bricks, burnt clay hollow bricks, burnt clay facing bricks, and concrete hollow blocks. And it is said others. But in part 5, chapter 2, many different types of, there are specifications of many different types of masonry units, like paving blocks. Paving blocks are also masonry units. So specifications regarding those materials are given in part 5, chapter 2. Last part not included in supplied material. That is true. That is true. I'll share that. So you can download again. I'll just after finishing this question answer session, I will share my new material with Dr. Prabhuto and Maria. I think they will upload again. I'm very sorry to Maria and Dr. Prabhuto to giving you trouble by
No
modifying
problem
the
at all,
slide.
Professor.
We wish to know about autoclave aerated concrete block, which is more greener. That is true. Autoclave aerated concrete blocks are greener in the sense that they are more environment friendly, but that is out of scope of this session, because this is actually I covered what is there in part 6, chapter 7 of the code. So there is nothing said about autoclave aerated concrete block in that chapter. So, and I'm not very sure if there is any detailed specification regarding this, even in part 5, chapter 2. So this is something we should include in coming updates of the code. Any detailing or recommendation for slender or high partition walls? So partition walls, there are not in BNBC. In ASC 41, there are some provisions regarding slender or high partition walls, but in BNBC, not even in the as in fields there is any mention of high partition wall, but for seismic zones 2, 3, and 4, if we just follow the concept of band, I think that will be helpful for slender or high partition walls. Maximum number of story or maximum height of a load-bearing wall masonry building, that is given. Both maximum number of story and maximum height, both are given. I showed a table, I'll show again. So stiffening, like where there is mention of cross walls, stiffening walls, there is some and that was in basic design requirements, right? Stability requirements, right? So here you see the height, story height is given, and for earthquake resistant building, this cannot, in any case, this cannot be more than 3.5 meters. So specifically that is also given there. And number of stories, height to width ratio of a building cannot be more than 2. And no table of this chapter has mentions about masonry buildings of more than 5 stories in height. So that can be implicitly, that is a kind of a limit. For wind uplift force, how do we connect the steel roof to the unreinforced masonry wall? So yes, there is a detailing on that. There is a detailing on that that is given in one section. I didn't include that. It is given how to anchor the roof with the wall. There is a specific detailing on that. You can find in the code. Sorry, I didn't include that. Which software is better for earthen structure analysis? Earthen structure. That is completely different thing. The BNBC 2020 does not cover earthen structure. BNBC covers bamboo structure, timber structure, masonry structure, concrete structure, steel structure, and steel concrete composite structures. Only these 6 types of structures, construction are covered by BNBC 2020. Earthen structure is out of the scope of BNBC. It will be considered as unengineered structure, non-engineered structure. So I don't know which software is better. Actually, if I don't know if there is any software for the earthen structures. If we would like to design a 2-story DRM structure, what load combination should we apply? Just for working stress design, follow part 6 chapter 2 load combination for working stress design. And if you design the shear wall or slender walls, then follow the strength design load combinations of part 6 chapter 2. Same. This is same for concrete, for steel, and for masonry. There's no difference. Is any profession given in BNBC 22 for earthen building? No. DSO's masonry bonded concrete floor having HSA it in practical existence. Floor have, I didn't understand your question, but masonry bonded concrete floor, you mean understand that concrete floor, those where you have masonry blocks inside the floor, inside the concreting. This was quite popular many years ago, this type of construction. But nowadays we don't follow that very much. And BNBC does not cover this type of construction. So practically they do exist. Practically they do exist in old structures. Can we consider infill URM bearing wall in the FEA model to evaluate existing structure? First of all, infill URM is not considered as a bearing wall. They are non-load bearing wall. And infill URM can be considered in FEA model by equivalent strat model, or there are other models too, but the easiest one is equivalent strat model. If the contribution of walls to take axial load in an RCC frame to be considered, what things to keep in mind? Can we think of bypassing some load from columns to walls? If that is so, what construction method is a must? I addressed this issue at the very beginning. It is very, very risky to consider gravity load taken by masonry walls in RC frame construction, because that is, they are incompatible from the point of view of flexibility. And since in the design of walls we don't want to consider the second order effects, but if we want to combine them, then we have to consider second order effects in wall design, and that is not easy. I mean, in that case you have to design walls quite thick, and that is not feasible or economical either. What will be the modulus of elasticity of masonry wall that is given? EM 750 root over Fm prime. In megapascal, if you express Fm prime in megapascal, Fm prime is the 28-day masonry unit strength, what you get from prism test. So 750 into root over Fm prime is the modulus of elasticity. Any detailing of recommendation for slender high partition wall? I have answered that question. What admixtures are used in the mortar of hollow concrete block, or why? To manufacture the concrete block? I don't know about any specific admixture that is used. But for concrete cement grout, again, admixtures are not used, because for grout, strength is not a big concern, because grout is not considered to be load bearing in that sense. That is, grouts are used for bonding purposes. So with high water content, water cement ratio, we can have quite workable grouts. So admixtures are not necessary, but if you want to have what do you call it, pumpable grout, then you can use super plasticizer to have more workability, right? But to manufacture hollow concrete block, I don't know what type of admixture is used. So we'll follow BNBC load combination to design masonry structure and reinforce. Yes. If someone failed a certain quiz but attended the seminar, why will not get any certificate from ICC? I don't know, Dr. Prabhupada, will they have a second chance by watching the YouTube videos? Can they appear at the quiz again?
I mean, this is the first time someone has asked for this. I do not know. And so far we have not given anyone a second chance at the quiz. So if we start giving them now, I mean, giving some people now, it would be pretty unfair to the people who failed before and did not get a certificate. when we have all the recordings ready, I do not know if, I mean, right now we are making the recordings available just for, for people to learn about the topics, but not for the purpose of receiving a certificate. Because with the recordings, we have a problem making sure that someone actually viewed it, as opposed to these live webinars. So, but we can discuss this, Dr. Rakib, in our own
Yes.
meetings to see if something could be done.
Right. There is one major issue regarding this is that the certificate is actually for CPD, right?
Yes.
And the CPD is actually used for getting paying certificate, and paying is provided by BPERB. So BPERB actually has to agree if someone can get a CPD certificate by watching a video. If BPERB allows, then probably that can be considered.
That's a good point. Yes.
Otherwise, this is not possible.
Yeah, even in the US, a distinction is made when someone attends a live webinar as opposed to someone who attends, just views a pre-recorded video. So yeah, it's a good point that BPRB will have to agree to that.
So there are issues, so we cannot answer your question right away, but we'll continue to discuss about this. So probably that was the last question. And okay, thank you so much. I'm so happy that I could answer all the questions. Not successfully, I could at least touch on all the questions this time. So thank you so much for attending this webinar. I know masonry structures are not very important for new buildings, but there are a lot of existing buildings, and there are many issues that you have already asked through your questions that we should think about. So that's why steel masonry structure, that chapter is relevant for us. Thank you so much.